So the first video from chapter 25 is going to be a little bit of motivation, and we're also going to define electric flux. Okay, so first off, we've talked about Coulomb's law. So we used Coulomb's law back at chapter 23, and we also used it when we were calculating electric fields. And right, so in principle at least, we can use Coulomb's law to find the electric field or the force due to any arbitrary charge distribution, right? So remember, if we've got a bunch of charges, we just do superposition, so we add up the contributions from each individual charge, or if we have a continuous distribution of charge, we can chop it up into bits and do an integral. Okay, however, in practice, dealing with those vector directions, right, because the force and the field are both vectors, so in practice that can be quite difficult, and right, if you have a continuous charge distribution that you have to do an integral over, in practice that can be pretty hard. So one of the ways to proceed, so if you look at the pictures here, which are from the textbook, so imagine you have a box, right? So in this, you've got some little box and you know what the electric field lines are. Well, the electric field lines that come out of that box tell you something about the charges that are inside the box, right? So you know if you've got electric field lines coming out of the box, you know there has to be a net positive charge of some sort. If you've got electric field lines going in, you know it has to be a net negative charge. And if you've got electric field lines passing through the box, that tells you that there's either nothing or just it could be neutral. So that's the whole idea and behind Gauss's law. But before we get to Gauss's law, we need to define electric flux. So this is where the box and the field lines come in. So electric flux is defined as the dot product of the electric field vector and the area vector. So and the electric flux is calculated through a surface. All right, so while we talk about an area vector, it might seem kind of weird to think of area being a vector thing, but you can define a vector for an area. So in the way, if you have an area, the way you define its direction is that it's perpendicular to the surface. So if you have, say, a flat surface, so this is my area, so it's just the area of this little pad of paper, so I can either define the area vector as pointing straight up or straight down. Now in practice for Gauss's law, we're going to be doing we're going to be calculating flux over a closed surface, and the convention is that if you have a closed surface, the area vector always points outward. Okay, so electric flux then, so we're going to use a capital Greek letter phi for electric flux, and we often use a little subscript e to indicate electric flux. We're also going to have magnetic flux eventually. And it's the value of the field vector E dotted into the area vector A. And if you remember from Physics 1 what the dot product was, so to calculate the dot product, it's the magnitude of the electric field times the magnitude of the area times the cosine of the angle in between them. So now this works if both E and A are constant. So constant in magnitude and constant in direction. So in general, if they're changing, then this simple E dot A becomes an integral. So you have to do the integral of the electric field E dotted into a little element of the area dA, right? And this works if the field is changing or if you have say like a curved surface like the surface of a sphere where the direction of the area is changing. So in units, of course, well, it's going to be units of field, which are newtons per coulomb, times area, which is meter squared. So the SI units for electric flux are the newton meter squared per coulomb. So, and here's a nice picture. So we've got some electric field lines pointing to the right. So here we've got some area, so that's perpendicular. So actually the flux is 0 since the area and the field are perpendicular to each other. And so the cosine of 90 degrees is 0. If it's tilted a little bit, well, then it's going to be some non-zero value, so EA times cosine phi. And if the surface is perpendicular to the field lines, then the flux is going to be a maximum, right? Because if E and A are pointing in the same direction or in opposite directions, then cosine 0 or cosine 180 is going to give you 1 or minus 1. So you get the maximum flux when the surface is perpendicular to the field lines.